right? That's a question about time. And that's saying, I start here, I'm going to end here, how long did it take me? And now, compare the 3 times. If you look at everything on these boards, except the very top, there is no reference to time, right? It's all about speed, height, stuff like that, nothing about time. So there's a limit to what you can get out of this approach. While it does have Newton there, we've done enough math to disguise a little too much of Newton. F equals ma can answer everything. We could go back to F equals ma and say, which ball wins? We have to deal with this kind of hairy math that I mentioned, but we could do it. And actually, I should point out that what you can do if you want to deal with the hairy math is you can actually use a bit of math which, probably if anything, you would learn more in economics rather than, we teach it for physics, but in terms of general stuff, it's actually more useful in economics, is what's called the calculus of variations. You can ask, which path, how should I build this track to get that ball to the bottom fastest? What's the optimal path? And so there's a way to do that, and it's using what's called calculus of variations, because it's an optimization problem. Economists use this for optimization, because if you think about what's happening, what's going on here? What's going on here is, here you've got an example, there's one back here, of a very steep decline. It's like you're letting the thing go almost in free fall. It's going to zip down really fast, but the price you paid is look how long this path is. Here you said, oh, the shortest point between here and here is a straight line. You've minimized the path, but at the expense of this gradual incline, where at the beginning, you have nothing like free fall. The speed's going to be fairly low up here. What works just right is this, and you can actually work out the mathematical form of that shape, where you kind of optimize and say, okay, I don't want it too steep, because then I have a very long path. I don't want it too flat, because then I'm not getting my speed advantage. This is just what I need. Okay? So, with calculus of variations and F equals ma, you can actually work that out. Okay? Energy will not do that for you. Okay, now let's do another demo. Actually, Jerry, you're all set to do this. Jerry's going to make a movie of this. So, this is going to be something similar, another race between 2 balls. This one a little trickier. The balls are going to start here, and they're going to be, see this one I just pulled down again, Jerry? I'm going to release the balls here. They're going to go zipping across, end up over here. But what you want to notice is, while they both go down these initial inclines, the one here stays on this flat track. The other one follows a longer path, down and then up again. The question is, which ball is going to win? Any guesses? I'm sorry? They're going to tie. Okay, that's certainly a possibility. And you would say why? What's your intuition on why they would tie? Right, so you could imagine they're going to tie, that even though this one's taking a longer path, right, we already, all this MGH stuff we've been talking about tells us that when this ball is down here, we're just moving ahead, when they're in this position, which ball is going faster? The red, right? The red has dropped farther, the red is going faster. So you might say, okay, it's got this extra distance, but it's got the speed. It'll, right, so they could tie. But, by the same token, anything is really possible. And it's really just a matter of how you build this thing and what will happen. So let's see what happens. Sorry, Ivan. The red won. Okay, one more time. So you can see how the okay, yeah, right. So one thing you can see very clearly is the red is moving faster there. Okay? But again, it's tricky. You could rebuild this. You could shrink this distance here, and then, in that case, you would expect the, what would you expect? I don't know, any guesses? play with this distance, what you would expect to happen?
Along the distance, the fire engine would be just further than I do it at.
Right, exactly, yeah, that's what I was blanking out for a second, but better I asked you guys. Okay, so, in other words, just to repeat, what David said is, if you make this part longer, then the red will win by an even greater amount, right? Because it has more time to make use of its speed advantage. So, in the end, the total distance that the red travels is unchanged, right? If I say that all I'm going to do is play with this segment, this length is fixed, that length is fixed, so all I'm doing is changing how I take the total, width of this thing and apportion it between the upper level and the lower level. Okay, so I can play with this lower level, I can imagine rebuilding this, and that will not change how far the red ball travels. But if I make this segment bigger, I'm letting red, get more advantage, right? It's got a longer run where it can use its higher speed to win even faster. But then I could imagine shrinking this. You see, red in this setup didn't win by that much. So I could imagine shrinking it and getting it to the point where the red would actually lose. That it has this longer total path to travel, and it doesn't spend enough time on that lower straightaway to beat the blue ball. Okay? Questions on this? So Jerry is filming this. Actually, you can send it to my son. So my son, who's now a sophomore in college, used to, and actually my daughter too, I used to bring them to help do lecture demonstrations, and this became, for some reason I don't understand, my son's favorite demo. So anyway.